Why did you even do that?
Pascal's law.
Pascal's law was discovered in 1647 by French mathematician Blaise Pascal during an experiment. A pole was vertically stuck into a barrel that was filled with water. As the water was poured into the tube, the pressure from the water caused the barrel to burst. Pascal's principle states that when a pressure is applied to a fluid at rest in a closed system, the force of pressure will be transmitted to all points throughout the fluid and its container. When hitting the lotion bottle, even though the center of the tube was punched, it is evident that the applied pressure is distributed all throughout the fluid. Pascal's law is modeled by the equations pressure equals force over area, and the change in pressure equals the fluid density times a gravitational constant times the change in height. Whenever the depth or density of the fluid increases, the pressure will increase. A change in the height and pressure of the fluid won't affect the density or gravitational constant.
We constructed our experiments from soda bottles, syringes, hot glue, and duct tape. We then needed to measure the amount of pressure we're putting onto the system. We found that we can do this by using a pressure gauge and a syringe. The pressure gauge told us that we were using about 30 psi on our system. For experiment 1, the materials we used were cola, water, a bottle, and 5 syringes. The variables height, pressure, and gravity depended on our independent variable, fluid density. We chose fluid density as our independent variable because cola and water have 2 different fluid densities. We realized that this difference could help us put Pascal's law to the test. To test this, we fitted a bottle with 4 syringes, equally spaced so the pressure is equally distributed. For one of the runs, we filled the bottle with water, making sure the side syringes were fully pushed in before we added the top. We then filled the top syringe with water, measuring it of course, and then screwed it to the top. We let go of the side syringes as we pushed into the top one. We then observed how the heights changed in the side syringes. We did the same process with cola in the same bottle. We filled the bottle with cola, making sure that the side syringes were fully pushed in. Then after pushing down on the top, we observed how the heights changed in the side syringes. We found that due to the higher pressure, more cola flowed into the syringes than water. For the second experiment, our materials were just water, a bottle, and 3 syringes. Our dependent variables this time were height, fluid density, and gravity. Our independent variable was pressure. We chose pressure as our independent variable this time because syringes at different heights have different pressures. This difference once again let us test Pascal's law. From this, we found that the lower syringe came out more than the upper syringe, proving that pressure has a direct correlation with the height.
To sum up our experiment, Pascal's law is working as expected. Pressure and height have a proportional relationship to each other. As the height increases, pressure increases and vice versa, while fluid density and gravity remain the same. However, we have to account for the experimental errors. The fluid besides water that we use is carbonated soda, which contains carbon dioxide gas, so it's also causing a little bit more pressure due to the air pressure. But overall, our experiment is a successful lesson proving that we do use Pascal's law in our everyday life.
Pascal's law applies to all hydraulic systems. Hydraulic systems rely on pressure to gain a mechanical advantage and accomplish their goal. A good example would be a braking system. The force applied to a brake pedal creates pressure in a piston cylinder system. Since the pressure is the same in a closed system, the pressure is translated to the wheels, stopping the vehicle.